Good afternoon. My name is Charas. I am a researcher at the Instituto de Telecomunicações, at the Organic Electronics Group in Lisbon, capital of Portugal. And today I will talk about the conductivity enhancement and improved water resistance of PEDOT PSS films via cross-linking with oxetanes. So for those of you who are not familiar with PEDOT PSS, this is the acronym for polyester ethylene dioxycycline polystyrene sulfonate, which is a conducting polymeric material composed of a pi-conjugated polymer PEDOT, which is positively charged and which is responsible for the conductivity and a negatively charged PSS, this being an insulating polymer, which provides also the solubility in water to the composite. This material is very successful in organic electronics due to a variety of properties, namely good electrical conductivity, usually around 1 Siemens per centimeter, tunable work function, electrochemical activity, high transparency in the visible range, high thermal stability, and easy processing, since PEDOT PSS is commercially available as an aqueous dispersion. These properties allow its use as an electroactive component in a wide range of new electrical devices, such as organic electronic implants, transparent electrodes, and skin electrodes. In such applications, two very important characteristics must be guaranteed: stability or resistance in aqueous medium and high conductivity. Regarding water resistance, PEDOT PSS pristine films are not very structurally stable against aqueous medium and may suffer from cracking, delamination, or redispersion. And to preserve the structural integrity, a common strategy has been the use of additives that promote cross-linking, such as GOPs, DVS, or glycerol, which results in the formation of polymer networks. On the other hand, the conductivity of pristine PEDOT PSS films are low for some applications. So the addition of conductivity promoting agents is a recurrent strategy also. They can cause screening effects on the PSS that in turn cause a phase separation between PEDOT and PSS, or conformational changes of PEDOT segments, also the selective removal of insulating PSS, or even decrease of doping. The most impressive impact on the conductivity so far has been obtained with the addition of strong acids such as sulfuric acid, although this procedure is highly corrosive and also requires relatively high temperatures. In this work, we show a new and simple method of cross-linking PEDOT PSS that simultaneously increase the conductivity in thin films on glass substrates. It also involves an oxetane unit, which we call HMO, which is low toxic, commercially available, and biocompatible. This is added to the PEDOT aqueous dispersion. Following their deposition by spin coating, the films are then submitted to a heating step at 100 degrees for 10 minutes under air. To test the resistance in water, we immerse the films into water and then we try again under the same conditions, the same heating conditions. And in fact, we have used, let me come back just to say that we have used two different PEDOT PSS formulations with different conductivities to test the feasibility of the methods to various types of PEDOTs. So we have used pH 1000 and PVP AI 4083, which I will call pH and PVP only for simplicity from now on. About the reactivity of AHMO in the medium of PEDOT PSS, Oxetanes units, they can undergo polymerization in acidic medium through a cationic ring opening mechanism, and they can produce linear or branched polyethers with pendant hydroxyl groups. These hydroxyl groups, they can react with the sulfonic groups from PSS, and therefore anchoring PSS to the polyether, therefore forming graft polymers of the polyethers and PSS, which we call here PHMO graft PSS. And in fact, we have proved the formation of these graft polymers of this type in our films. As seen here, films prepared from mixtures of HMO and the PSS were investigated. In the red spectra, we see that the peaks of HMO, they disappeared, and the peak assigned to PHMO appear. And here at close to 4 ppms, there are the peaks assigned to the ether linkages anchoring the sulfonate groups of PSS. By analyzing the films of the liquid mixtures of HMO HPSS, we also found that neither the graft polymer nor the esterification reaction occur in the liquid state, because the spectrum is the spectrum of PSS plus HMO. Which leads to the conclusion that these reactions only occur in the film during the annealing step. Now, going to the properties of the films, the measurements of their thicknesses before and after water immersion were used to quantify their structural stability in water. Looking at the pristine films, we can see that pH loses close to 40% of the thickness when immersed in water, so the pristine polymer. And for PVP, the thickness that remains is almost zero. Moving on to the films now prepared from the mixtures with AHMO, we see that the loss in thickness when the films are immersed in water is much lower in both kinds of polymers. There is also an effect on the thicknesses, especially in the case of PVP, for which the higher contents of AHMO lead to lower thicknesses, but always associated to a higher stability. The electrical conductivity of the films was also measured. This was made using a 4-point probe technique over gold contacts deposited over the films. We can observe that the electrical conductivities of the pristine films is relatively low, as expected, but the addition of approximately 2% in volume of AHMO causes a high conductivity increase in both types of films. In these sets, the optimal AHMO content to obtain the maximum conductivity represents 294 times more than pristine films for the PVP and 1,475 more times for the pH case. This last increase resulted in films with conductivity around 300 Siemens per centimeter, which is well comparable with films obtained when PEDOT PSS is treated with glycerol. But in this case, a much higher temperature is needed, above 180 degrees. So for certain applications, it's also important to evaluate, as I said, the transmittance or transparency of the films. So here I show examples of the transmittance of the most conducting films with the HMO in comparison with pristine film, with films from pristine PEDOT. As we can see, the films prepared from the new formulations keep their transparency up to 900 nanometers in wavelengths, and exhibits even higher transmittance than the polymer pH So we also went to investigate the film's by Raman spectroscopy to evaluate possible conformational changes in PEDOT change, which could be associated with the increased conductivity. In fact, on the spectra, looking at the region where PEDOT segments are active, we can see that in the films prepared with HMO, so these red and blue peaks, in the films assigned to the C-alpha, C-beta double bonds in the tailfan rings, the peaks gets narrower, which is attributed to a more crystalline sample. Also, there is a decrease in the relative intensity of the surrounding peaks, which is in accordance with conformational changes in PEDOT chain segments from the benzoid structure to the quinoid structure. This last is the more favorable for the transport of charges at both inter and intra-chain levels. And analogous results were found for the other kind of PEDOT, in this case pH, indicating the analogous effects on the conformational changes. So it was also interesting to investigate the film's surfaces by atomic force microscopy. We observed that the films of PEDOT with HMO show very different surfaces from the films prepared with the pristine polymers. Before immersion in water, the film surfaces are grainy and presents contrast in the phase image, indicating the presence of a different component. After immersion, the surface in water, the surface returns to a smooth surface. And we also wash the films with deuterated water and perform the proton NMR, and we identify the polyether PHMO in the DTO, meaning that this polymer is responsible for the grainy surface and can be easily removed, at least in part. So in view of these results, we propose that formation of the graft polymer of PHMO and PSS causes a weaken in the interaction forces between PEDOT and PSS, because PSS loses their negative charges by reacting with the hydroxyl groups of PHMO, and that promotes a phase segregation of PEDOT chains, thereby forming more closely packed domains and more ordered domains, where the transport of charges is facilitated and the conductivity is increased. We are now exploring different oxetanes additives, but also exploring applications of these films. The first is the replacement of the transparent electrode made of indium tin oxide in organic photovoltaic devices. The replacement of this electrode by more sustainable materials is a topical issue because of the the lack of availability of indium, and therefore it's a high cost also in the market. So as you can see in the devices, ITO is typically covered by a layer of PEDOT, PSS, PVP, acting as a whole transport layer. So what we did was to replace only the ITO layer by the most conducting formulations that we have developed, and cover it with regular PEDOT, PSS, PVP. We obtained devices operating with similar current flows, although the fill factor is lower, and also the open circuit voltages are decreased, and therefore this resulted in lower efficiencies. This work is still under course, and by using other oxetanes, the conductivities can be further increased, and hopefully we improve also these results soon. So in conclusion, a new cross-linking method of PEDOT PSS has been developed that allows an increase in stability in water and an increase in conductivity. This approach involves the addition of an oxetane derivative to PEDOT PSS, causing PSS to cross-link and also causing more crystalline PEDOT domains. The potential application studies so far are as transparent thin film electrodes. And so to conclude, I would like to acknowledge for funding FCT from Portugal mainly, and for those who participated in this work, my PhD student Sara, Professor Luís Santos for the Raman spectroscopy, and Professor Adelino Galvão and Professor Jorge Morgado for discussions, and thank you all for your attention.